All right, so here's another one. Again, we're drawing influence lines. This is going to be the moment at C. There's C kind of in the mid-span there. So like we talked about before, since I'm going to try to find the internal moment at C, you can imagine a section cut here. And thinking of method of sections, would you rather work the left side or the right side? Left, I think less reasonable. There's really no major advantage of going either way. So as I cut it, and I want the internal moment here, I'm going to have to deal with the reaction at A. So the first thing we need to do is find the effect, the influence line for A. So I'm going to draw my body, free body. I'm going to assume a reaction at A and one at B. And I'm going to imagine my unit load at some position X along the beam. And I want to find AY. Let me put these dimensions here. This is 10 feet and 5 feet. So how to find my reaction at A? Okay, we need some moments about B. And you can see I need to know the distance from B to the unit load. What would that be? It's going to be 10 minus X. See that? Which is kind of interesting too. What happens if X becomes 15? 10 minus 15 is negative 5. See, it'll switch directions automatically. So now if I sum moments about B, my reaction at B, make sure it's in equilibrium, I can find my reaction at A in terms of the unit load. So what's the moment of the unit load? Positive or negative of this sign convention? Positive. So there's my 1. And then the distance, 10 minus X. And then the AY reaction creates negative moment and has a moment arm of 10. So that means that AY is going to be equal to 1 minus X over 10. Notice when the unit load moves all the way over to X equal 15, what does my reaction turn into? Negative. Does it make sense that my reaction now is down when I'm applying the unit load here? I think the answer is yes, because you'll notice it's like a seesaw. About B, if I push down here, I better push down here to balance it. So that seems to work. So now I can go back and look at my moment at C. So when my unit load is between 0 and 5, that means I am on this section AC. I know my reaction at A. I just solved for it. It's 1 minus X over 10. Here's my positive bending moment at C. Let's see, what else do I have? This is 5 feet. And then I'll have my unit load at some position X. So what's this distance here? 5 minus X. So I have all the pieces I need to find the moment at C. So I will sum moments at the cut, in this case C, make sure it's in equilibrium. And what do I have? Well, I have the internal moment with my sign convention, that's positive. What about the unit load? Positive or negative moment? Positive. So force is 1, moment arm is X minus 5. And then the reaction at A, positive or negative moment about C? Negative. So the force will be 1 minus X over 10. And what's the moment arm? 5. So if you solve for the moment at C, what do you get? Well, there's 5 minus 5. That cancels. And I got negative x minus plus x over 2. So I've got negative x plus x over 2 is negative x over 2. I throw it to the other side, I get positive x over 2. Okay? So that was from 0 to x. So what about from 5 to 15? Well, I can use the same free body diagram as we did before. I have the same internal moment at C. I have the same reaction at A. It's the same length, 5. What's changed? The unit load, which was somewhere between 0 and 5, is now between 5 and 15, so it's not on this free body. All right? So I sum moments here. At the cut, make sure it's in equilibrium. We'll do it again. Again, the internal moment is positive. There is no applied load anymore, and I just have the reaction at AY, which is negative moment, with a force of 1 minus x over 10, and a moment arm of 5. So when you solve for the moment at C, you get 5 minus x over 2. I just have to plot it. So now I have my moment at C as a function of the position on the beam. So there would be point C. There's 10, there's 15. So from 0 to 5 feet, what equation do I use? I use this one. So at x equals 0, it's 0. When x equals 5, it is 5 divided by 2. And that's linear. And then from 5 to 15, I use this equation. When you plug in x equals 5, what do you get? You get 5 minus 5 over 2. You get 5 over 2. So that matches. And then you continue forward. If I put in x equals 10, I get 0. I put x equals 15, I get minus 5 over 2. So, if I weigh 1,000 pounds and I'm a car tire driving across this structure, where do I go to create the maximum moment at C? Well, now you have to think about it, because in one case it's positive, and in another case it's negative. Magnitude's the same, but direction changes. So now you have to be careful, especially with moment. It's where's the maximum positive moment, where's the maximum negative moment. So I'll define my question. Where's the maximum positive moment? Where do I stand to create the maximum positive moment? Looks like I stand right at C. And if I weigh 1,000 pounds, it would be 5,000 divided by 2, or 2.5. Thank you. And then if I want to, so that means I'm standing right at C to create the maximum moment, positive moment at C. That makes sense. You put a big load here, you're going to get a big happy face, right? Positive moment. Where do I stand to create the largest negative moment at C? All the way out here at the free end. So if I push down here, the beam bends up into negative shape. It's the same numerical value just because of the values in this problem, but it does change sign. So that gives you some indication in structures that as trucks or any live load moves across the structure, at a particular point, I'm constantly moving between positive and negative moment. That means the structure's moving up and down, which means it's vibrating. So those live loads really cause the structure to vibrate. I don't know if you've ever had the opportunity to stand in the middle of a span of a bridge, maybe while your car is disabled, which is a horrible thing to do or to be. But take the advantage while you're there and feel the way the bridge changes as it vibrates and changes shape as a big truck goes by. It's quite impressive. You can really feel it. In fact, it's a little scary because the vibration is so much. It's changing so much. You can feel the vibration. Of course, the displacements are hundreds of inches, but it's going from positive to negative. Your body can really sense that vibration. I once had the opportunity to stand in the middle of the I-40 bridge across the Mississippi River.
Me too.
Not because of a disabled car. Were you disabled?
No, I was watching the fireworks on the 4th of July.
They let you go out on the bridge?
No, but like everyone had stopped on the bridge. So we were stopped.
I was out there during normal time. About 10 years ago, they were rebuilding the bridge. I don't know if you guys remember, they had lane closures a lot. So we went out there and did a little tour. So I was standing in the closed lane at mid-span as, fully loaded tractor-trailer trucks went by. It bounced. In fact, we had the trunk hood of the car open to get stuff out, and the hood started going up and down. And it actually slammed shut one time when a couple of trucks came by at just the right time. So it really moves a lot more than you think. But when you're in the car and you're driving across it, you don't feel it because of the suspension and the tires. It really muffles all that. But when you're standing there, feet on the deck, you can really feel it. It's quite impressive. All right, so that one took 11 minutes, even with my yapping about the bridge. I've also had the opportunity to get up underneath normal bridges and be able to put my hands on the bottom of the beams as vehicles go over. You can really feel it too. So I'm not saying, go compete with the homeless guys to get under the bridge, but if you have the opportunity to take advantage, especially if there's a lot of truck traffic, because you can really feel it. Because those things fully loaded can be in the order of 80 or 90 kips, like 100,000 pounds. So it's a lot, and they're moving at a high speed. You really feel it. Cars, not so much. But you can really, especially if you're at the point where they're coming off the roadway and first entering the bridge, which is probably where you could be if you could put your hands on the bottom. You're probably on the abutment part. That's a big bump as they come off. They kind of bounce onto the bridge. Approaches are notoriously bad for deformation, and TDOT usually refers to them as the bump at the end of the bridge, and they laugh. There's nothing they can do about it. But you probably notice every time as you go onto a bridge, there's a bounce, and then you come off, there's a bounce. The bridge is solid. It's usually the approach stands that are settling and moving around. That's the bump you feel. And there's nothing to do but just fill them in and keep patching them. Super exciting stuff, huh? All right, let's. What if you don't have a moving load per se? What if you have a distributed load that represents something moving? So there's a way to use this influence line, even though it's built for a single moving load. You can also use it for a distributed load. So we already know from our discussion that if you have a concentrated force, it's easy. Since we're using the unit force, a dimensionless force, all we have to do is multiply the actual value by the information on the influence line. So just take the position, multiply by the magnitude of the actual force. What if I had a concentrated or a uniform load, not a concentrated or a uniform load? So in that case, if you look at a bridge with a uniform load on it, so why would I consider that in my load? Well, think about it. The bridge has some weight, and then somebody comes along and adds to it. So this can contribute to the live load, even though it looks like it's a dead load. Also, a lot of designs for bridges, trying to model every structure or every vehicle that passes over the structure is kind of challenging. So the design codes allow you to represent all the live load traffic by a uniform distributed load on all the lanes. You can still use your influence line, but now how do you handle it for uniform load? It's not as bad, it's not as hard as you think. If we look at a little differential bit, say dx of the structure, right there, and then I look at all the pieces that act on it, you'll get this. So here's the, remember this is maybe an influence line for something, and then here's our little dx part of it. This is the applied load. Well, I can come up with a equivalent for that differential force. It's just the magnitude of the distributed load times dx, right? And it's at some position, that's the same position x. So all I have to do is integrate all these little differential forces up, and at each point where I have my differential force, multiply it by the value on the influence line, y. Of course, if I integrate that to get the total effect, since this is a distributed load that is constant, the w pops out, and you're left with the interval of y dx. What is y dx? Well, y is the value here. So this just represents the area under the influence line. So the total effect would be the value of the uniform load times the area under the influence line. And all of our influence lines are either rectangles or triangles, so it's really easy to compute that. So let's use that to our advantage and work this problem. So now I have what's called a dead load, 70 pounds or so of force per link. A single live load of 10 kilonewtons, that's the one that moves around. And then we have a dead load of 1.5. So that's our uniform load. And then there's our live load. And I want to determine the maximum negative moment at A. So let's do that. Hopefully I brought that problem. I don't have to redraw all that. Oh, I did. So this combines not only the stuff that we've been doing about influence lines, but also kind of a little more practical application of some forces.